Really a pleasure to be here back in the UK for the first time in quite a few years, and thank you very much to Ed and all of the team at Hutchinsons for the invitation to be here, and of course all of the behind-the-scenes work that we all know goes into putting on an event like this. So thank you very much, and pleasure to be here. So today, actually, the theme of the conference was making the transition, and so I actually thought I would talk a little bit about some schools of thought. How do we think about approaching transition? And we'll do this through a bit of a case study on nitrogen. And I think that, there's many ways in which we could talk about transition or do that transition. There's many ways, and we had some questions there earlier that really kind of really focused in on this. All farms are different. What works one area is going to be different from the other, etc. There's no set roadmap per se. It's nuanced, it's different, and we have to therefore take that kind of approach. So there's many ways to then approach that transition, and I'm going to talk about one of those called efficiency substitution redesign. And I'm a big fan of this. I think it's just a really nice way to think about taking those steps. We all know that taking steps into the unknown can feel very risky in terms of the risk exposure to the business, etc. So I think ways in which we can really plan that kind of stepwise approach through that transition, I think, is always a very useful tool. So we're going to explore what this means. And really, so it is a way to conceptualize that transition from our current production systems towards something more sustainable, whatever we want to call this, regenerative, agroecology, etc. So it's a way to think about that. And there's three distinct steps in this framework called efficiency, substitution, and redesign. And I'll just kind of read a few things here to kind of set the scene here. But if we kind of think about conventional agriculture, it's often we would talk about it's very much built around the discipline of agronomy, often very input dependent. We use a lot of course, science and technology to manage. We kind of consider it that the fields and the farm is a system that is under our control, and we use inputs and we use tools to monitor and manage and control that system, which is not really how natural ecosystems work. And if we want to kind of have this discussion about agroecology, looking into nature, some element of biomimicry, looking at natural processes and trying to harness them and mimic them and bring them into the design of our agricultural systems, we have an immediate kind of juxtaposition there of the classic kind of agronomy of system under control versus working with natural cycles and systems. Now, of course, that's very easy to say, of course, but always much harder to do in practice. We can't expose ourselves to that risk either. But then again, you're all farmers, you're already at the mercy of the vagaries of the weather. You're already under that pressure. So actually, something that we always consider as such a negative impact, the weather and as we talked about earlier, too dry, too wet, too this or whatever. This is something that happens already in our businesses. So actually trying to implement systems to work with that can also spin it on its head and be very advantageous. So therefore, we then think about, okay, efficiency, substitution, redesign. What does that mean? Efficiency really then says, okay, let's optimize the current model that we have. Let us be as efficient as we can be. Let us use the least amount of fertilizers as possible. Let us use the least amount of plant protection products as possible. Let us use the least amount of diesel as possible. We're still using all of those inputs. We're still managing a conventional system, but it is a high efficiency, low input, high efficiency system where we are using very small amounts of those very high efficient inputs. Then we could think about a next stage of this transition, which was called substitution. And this is where we could say, okay, now I've been so good, I'm using all these strategies to use less, to be very efficient and use the least amount as possible. Now it therefore becomes easier to drop it, because you're already using a small amount, so we can cut it out and substitute. We substitute into alternative practices or alternative inputs. Biological inputs, softer inputs. It depends on the context of what we're talking about here. We'll do a nitrogen case study in a second. So that's that point. We've used less and less as possible, being efficient, then we substitute out into alternatives. Okay, and we can have debate about that too, but that's the core of the idea. And that really then makes way into the final stage of redesign. And really what redesign is all about is it is the core of agroecology. It's about redesigning the production system to decouple that input dependency. We want to decouple that. We want to make agriculture and food production compatible with nature. It's about nature-friendly farming. It's about biodiversity-based agriculture. It's using ecology, ecological principles, using biodiversity as an asset to then also grow food and produce, have a productive system to produce food. And so we have, in that redesign stage, we have decoupled that input dependency. We are using the natural cycles. We are harnessing the ecology toward food production. And of course, it's a beautiful shared goal. That's essentially kind of, you could boil, agroecology is actually a very broad and complex topic. We've had a really a thin snippet of that today. It is a very, very big topic, but if we could boil it down to a very simple definition, ultimately it's about producing food and taking care of the ecology at the same time, shared mutual goals. So that's kind of then a way to think about this. Let's be hyper efficient, let's substitute out, and then let's redesign using biodiversity, nature-friendly tools, etc. And it's really, the thing about this school of thought is that one thing we have to be very careful of, and I'm a big fan of the efficiency and the substitution phase. I think these are really important first steps. They're very important in that transition, but we must be careful not to get trapped into those two stages. We have to be taking the steps ultimately into redesign. It is redesign that is really going to make bigger impact and bigger change to the farming system. The potential gain, the potential win, or the sustainability potential of the first two stages, they are fundamentally important because they get us on that road. They're helping us take those steps in the right direction. But their potential for true, deeper impact of the land is minimal. It is really the redesign element. And that's because, again, it's mimicking nature. And as you all know, natural ecosystems, they often work in virtuous cycles. They ebb and they flow, and they lay down one after another, year after year. And over time, we see enhancements of the natural ecosystem, the quality of that ecosystem. So they are much more virtuous in their cycles and therefore have much greater potential. And really what we're talking about when we think about an agroecological farming system is also this word, multifunctionality. That's really what we are striving to achieve. Our conventional intensive input production systems, yes, they are very good at being productive. They're great at producing crops, producing meat, fiber, whatever. But they're not necessarily always quite so good at some of the other providing other ecosystem services, like whatever, water control, of course, the big one here, pest control, climate, soil, nutrient cycling, recreation. We just heard great examples from Ben bringing in an element of recreation. So farming systems typically are not so good at those things, but of course they are very good at being productive. Now, if we think about a natural ecosystem, it's the reverse. It's good at providing some of those ecosystem services and all those other benefits, but of course, they're not typically as productive. And so, of course, obviously, we have to strike a balance somewhere in the middle of this discussion. We can't have one extreme or the other. And that's really the future of farming. It is going to be more thinking about multifunctionality, designing farming systems that are productive, but are also supporting the landscape, supporting the ecosystem, etc. And another way to kind of think about this is, I really like this image too. If we think about, we used to have this classic debate between organic and conventional, and we used to lock heads so much on these two sides of the debate, and it's fascinating to see how that's changed in recent years. There's so much in the middle ground. There's so much collaboration and potential and bubbling up in the middle ground, what we might call some kind of a hybrid system. Everyone's interested in soil health now. An event like this could be full of equally conventional or organic farmers, and everyone's just as interested in soil health or earthworms or the latest soil biology or this or that or whatever. It is universal. It has applicability. And that kind of classic, I think, debate that we used to see, I think it's great that is really kind of melting down. It's not quite such as fierce as it perhaps once used to be. And I think that a really important point about this is that it really doesn't matter if you consider yourself, I mean, it's just a label at the end of the day, but like if you consider yourself to be organic or conventional or regenerative or something in the middle along this kind of bottom axis, it really doesn't matter. All of those production systems would benefit from more ecology, from bringing in more ecological design, bringing in more diversity, more biodiversity. And that will benefit an organic system, that would benefit a conventional system, that would benefit a regenerative system. It really doesn't matter. Everybody can design with more biodiversity into their farming system, irrespective of where you're starting from, irrespective of your farming system. So that's, again, all about biodiversity conservation, ecosystem services, and, mixed farming systems are a good example of that. Integrating crops and livestock, exactly what happens in a natural ecosystem. We don't really see plants existing in isolation in nature. They're always in concert with some form of animal life, and I think that's a really simple and good example of where we need to go. And so I think this picture then is just helps to kind of create a visual in this context. Here on the left-hand side, probably classic scenes out of the prairies in North America or Australia, vast areas, a very simplified landscape, very potentially monocultural or very low diversity, what's generally called a biologically simplified landscape. Vast areas of the same thing. And on the right-hand side, we have pictures that maybe are much more common for here in Europe, where we have, different size fields, small fields, some are green, some are brown, some are light or dark green. We have hedgerows, we have other pieces of ecological infrastructure here that are all bringing benefit to the wider landscape view. And that's really what redesign is all about. On the left-hand side, these two images, these production systems, we could have gone through the efficiency stage. We've used less and less inputs, and we're using barely any, and that's excellent. We might have substituted out of those, and now we're using some biologicals or biostimulants or some other softer option. That's great too. You're being really efficient. You're making as small a footprint as possible. Great. But it is still a biologically simplified landscape. You haven't brought in the redesign element, the ecological infrastructure like we see on the right-hand side. And this is an example of what I mean. We have to be careful about getting trapped in the efficiency and substitution phase. If we really want to see true restoring landscape health and functionality, we need to be thinking more along these lines on the right-hand side here. So let's explore a case study. And again, this is just one kind of way to think about this. And there's many ways in which we could interpret this nitrogen case study, but I'm just going to choose a few examples to kind of go through to illustrate, put some practice into the principles here. So efficiency, I'm going to use an example of let's use foliar nitrogen applications to help us reduce the nitrogen that we apply to the soil. Of course, we know nitrogen is very reactive. It can leach through the soil. It can volatilize off into the atmosphere. So the less we can put down into the soil, the better. And one of the ways in which we could do that would be through targeted foliar applications instead. So we're going to talk about that. And then the substitution phase would say, okay, I'm using less nitrogen now. I'm doing things like foliar tricks. Now I might be able to substitute out of that and use some kind of a nitrogen-fixing bacterial product, some kind of a bio-fertilizer and fixing type product. That could be a next stage. And then the last stage, a redesign, would be then, okay, well, let's diversify that simplified landscape. As we all know, typically very cereal-dominated. Let's diversify with legumes. Let's integrate legumes. That is a redesign element that brings the diversity back into the system. And of course, we can then harness the natural process of nitrogen fixation that those legumes do and harness that towards a production goal. So this is an example. Let's have a quick kind of explore of this. If we talk about then how do I be more efficient with nitrogen, with the inputs that I do, with the nitrogen that I do use, how do I be the most efficient I can be with it? And there's two kind of ways to think about that efficiency. One is simply the amount that you use. So we want to try and use less nitrogen or therefore minimize the losses. So that's kind of one piece of the puzzle of efficiency. Or we want to maybe think about the form of nitrogen. What is the most efficient form of nitrogen that we can then also use towards a production goal? So let's explore both these two. feeding through the foliage, there is great potential to use less nitrogen through a foliar. When you apply foliar nitrogen, you are targeting that nitrogen directly into the leaf, directly into the crop. In doing so, you are applying less to the soil. And it is when nitrogen touches the soil that it becomes so reactive. Of course, it can convert to nitrates and leach through. It can also then be converted to ammonia, as we talked about, and off gas. Those processes are very significant in the soil. Firstly, leaching doesn't happen off the leaf, so you have zero leaching off the leaf, but you do have some volatilization off the leaf still, but it is much less off the leaf of a plant than once that same nitrogen is in the soil. So straight away, the opportunity for foliar nitrogen is exactly that. We are targeting lower doses, targeting them directly into the foliage where that nitrogen gets into the plant. Once it is in, it's stable. It's not going to be so reactive. It's not going to be lost so easily from the system like in the soil. So that's fundamentally kind of one basic example. Now, foliar nitrogen is a big topic. I can't just say to you, oh yeah, just go and do foliar nitrogen, you're going to be fine. There's a lot of nuance to it. We could do a whole hour-long session on this, or even a full day. There's many factors that go into the design of a good foliar spray. There's many considerations. It's not the kind of the point for today's discussion, but we're trying to take a more broad view at this. But I will acknowledge that there are many factors to consider. It's about the formulation. What do you put in the spray tank? What form of nitrogen? What other stabilizers or enhancers, inhibitors can we also include? Other supporting nutrients that help nitrogen function. There's many factors. The spray pH, all of these things are really important that we could kind of take a deep dive into. But I acknowledge, just trying to acknowledge that, yes, there are many variables at play here. Then we want to apply it, so that's really important, making sure you've got the good correct choice of nozzles, the right spray pressure, making sure that that nitrogen hits the target. Okay, that's also very important. Okay, what is the crop? Sure, this is also important. Some plant species are more responsive to foliars of nitrogen than others. For example, waxy brassicas have the waxy leaves. So, generally plants with those very waxy leaves are a little less responsive to foliar applications than non-waxy plants. Again, not that that is an insurmountable challenge. We can include wetter stickers and spray oils to help kind of overcome that. But again, just pointing out there's nuance with different crops. And the big one, absolutely environment. Environmental factors drive the uptake of the foliar nitrogen. So the big one here is the time of day or the humidity. Foliar nutrients are absorbed much more effectively under high humid conditions. So you want to be targeting foliar sprays in the early morning or the late afternoons, for example, when we have high humidity. High humidity is absolutely central. It's key to get for those nutrients to pass in through the leaf into the plant. And if we don't have good humidity, and I'm talking really anything from 70% upwards, then that nitrogen is more prone to just sitting on the leaf. And the longer it sits on the leaf, yes, then it can potentially be washed off or volatilized off. But the quicker we get that nitrogen into the plant, the less losses we're going to see. So I share that just as a very quick summary to say there's lots of factors. And I'll give a shameless plug here. Next year, from the mid-Jan to mid-Feb, I'll be running an online course specifically on foliar nitrogen. It will be a 4-week course, very deep and detailed discussion of this topic, with the broader goal of how do we use foliar nitrogen to improve our nitrogen use efficiencies and ultimately use less. Of course, very topical topic at the moment with fertilizer prices and the push on nitrogen reductions, etc. So please follow my social media or sign up to my mailing list for information on that. Okay, so then also what about things like stabilizers or inhibitors trying to keep nitrogen in the more stable forms, or using other strategies like applying a carbon source with the nitrogen. And really what that carbon source does is kind of like a sponge, and it binds to and wraps up the nitrogen and helps to stabilize it. Makes it now a bigger molecule that's less leachable, less likely to volatilize off. So again, just little examples of tricks, little small incremental steps pieces of the puzzle that can all ultimately help us be more efficient, use less, and or minimize those losses. Okay, so let's then think about the form of nitrogen, efficiency from the form. What does the plant really want nitrogen for? What does it do with nitrogen? One of the really important things, there's lots of things of course, but one of the really important things that you're all aware of is to build protein. Protein is really great to enhance quality, but all sorts of other plant health related aspects too. So when we feed nitrogen to the plant, if we use ammonium nitrate, for example, nitrate can come into the plant. If we use urea, urea can be absorbed by the plant. Both of those two forms of nitrogen have to be converted first into ammonia and ammonium. And of course, we can apply ammonium directly in as well. So these are commonly used forms of nitrogen, nitrate, ammonium, or urea. But the plant doesn't really want either of these three. It doesn't want that at all. It wants organic forms of nitrogen. It converts those into amino acids, and then it joins them together to convert that into proteins. This is really what the plant wants. This is the metabolic pathway, the kind of the conversion flow, the chain, in which nutrients, nitrogen here, are ultimately absorbed and then converted into protein. So the point here is to say that the plant doesn't really want these kind of inorganic forms. It wants organic forms. That's why it's a living organic organism, biological organisms, we heard also this morning. So it's on its way, as it grows, as it's producing, it is turning the raw foods, the raw ingredients, ultimately into plant food, plant bodies, plant biomass, but specifically proteins in this example. So therefore, along this conversion, some forms of nitrogen are more efficient than others. And let's have a look first at an example of nitrate versus ammonium. You can see that nitrate is further back in this flow, in this metabolic pathway, versus ammonium. So when ammonium comes into the plant, it is a single little step there to go from ammonium into glutamine. This is the very first amino acid that the plant will produce. So it's a one-step process to turn that ammonium ultimately into glutamine, the very first amino acid, which then can get turned into all sorts of other amino acids and build protein. Conversely, as you can see on the other side with nitrate, when nitrate comes into the plant, actually first that nitrate has to be reduced to nitrite. This is an energetic step that the plant has to process that. Then the plant turns that nitrite into ammonium. And then the plant turns that ammonium into that amino acid, the glutamine. So you can see here we have a multi-step process ultimately to get to the same result, to that first little amino acid. And then from there, we would go onwards and build the proteins. But you can see that in that chain, one is short and one is long. And that means that each step of this chain is a metabolic or energetic cost to the plant. The plant is expending energy to do each of those steps. And the more steps that you have to do, of course, there is a greater drain of energy for the plant. And it could be using that energy for other growth processes. It could be using that energy elsewhere. So straight away, actually nitrate is not such an efficient form because it is very metabolically expensive for the plant ultimately to turn it into organic nitrogen, into those amino acids, versus ammonium, for example. Okay, so that's part of the discussion. Beyond that, we could also go into the deeper discussion about the nutrients that are required that support this process. So, for example, manganese and magnesium are both essential to help this conversion. We need those other beneficial synergistic nutrients to make this work. And with the other pathway, with nitrate, you can see that there's a lot greater nutrient demand, a greater nutrient drawdown to go through this pathway. So molybdenum and sulfur are very important here. We need iron for this step, and again, we need magnesium and manganese for this last step. So not only is it a drain of energetic cost, a drain of energy for the plant, we can also see that the nutrient requirement is also greater through the nitrate pathway because we need these other nutrients to help along this chain. So straight away, and I could go back to this chart here just to kind of summarize that. These are the nutrients that are required in each of these steps. So we need moly, sulfur, and iron, as I just mentioned. We need nickel to process urea. We need magnesium and manganese to get that amino acid, that glutamine. And then from there, we do need lots of other nutrients ultimately to build all the diverse array of proteins that we see in plants. So particularly the top three here, phos, sulfur, and mag are really, really important for good protein synthesis. But equally, again, manganese, boron, potassium, and zinc play a role. Okay, so I try to summarize that really quickly just to point out that when we talk about managing nitrogen, we're not just talking about managing nitrogen. You also have to be thinking about all of these other essential nutrients as well. They are also called essential for a reason. The plant cannot complete its life cycle without them, so you need to be thinking about these. It doesn't mean you have to be applying them, but you need to know that they are present in adequate amounts to also to support and facilitate this metabolic pathway. So there's one piece of the puzzle, nitrate versus ammonium. Ammonium, a lower, higher efficiency form, a lower energy intensive form. But what if we think then, kind of re-representing that image and kind of just in a different way here, as we kind of move into the discussion then about the organic half. Again, the plant doesn't want ammonium or nitrate or urea. It doesn't want those. It wants to build amino acids. It wants to link those amino acids to build little amino acid chains called peptides, and then it stitches those together ultimately to build the more bigger, complete, and complex protein. This is what the plant wants. So then if we have a question about, well, what is the most efficient form of nitrogen to feed the plant? If the plant ultimately wants to be here, and we are always feeding it the inorganic forms, again, there's this constant energetic drain to build that protein. So what if we just gave directly to the plant protein, or peptides, or amino acids, any of these little three at the bottom? What if we just gave the plant organic forms? Same deal again, this is called metabolic shortcutting. Rather than go back down the chain, which is going to expend more energy to get to the top end of the chain, why don't we just deliver nutrients in the organic form already and again save the plant's energy? It doesn't have to expend energy on all of this processing of the inorganic forms. We're just going directly in with the organic forms. And so this is then the answer to this question. Organic forms of nitrogen are the most efficient. They are preferable from this point of view, because they save the plant's energy, and when we are saving the plant's energy, the plant can use that energy elsewhere for other growth processes. So consequently, examples of organic forms of nitrogen that we could be feeding to the plant in a liquid form, it would be things like fish hydrolysates or protein hydrolysates, amino acid-based products. There's lots of these types of things out there. And in a dry kind of soil-based kind of application, things like compost, manure. These are all organic forms of nitrogen as well. Some of our biosolids, etc., some of those would have some element of organic forms. So there's one simple trick that we can do is just try to lean towards feeding the plant more of these organic forms. So protein hydrolysates, compost, manures, etc., is going to help feed the plant more of these types of forms. And this is an emerging piece of rethinking about plant nutrition that's happening at the moment. This is a really nice image from a very recent review paper just published last year on this, is that again, the classic traditional view has been really heavily focused on the inorganic forms, but we now know that yes, the plant can take up more complex forms. Yes, amino acids can be absorbed directly through the roots. Yes, bigger proteins can be absorbed directly through the roots. Yes, the plants can access these organic forms of nitrogen. It's just that in our traditional view of plant nutrition, we've been very dominated in our thinking about the inorganic forms and managing those. But now we are beginning to understand that actually the plants can absorb these larger, more complex molecules, these organic forms directly. And even beyond that, plants can even absorb bacteria, whole microorganisms themselves, which they can also use for nutrition. So the point is that we know a lot less about this. This is emerging thinking. It's a rethinking of the old kind of basics of plant nutrition where we were heavily focused on simple inorganic ions. Now we are beginning to understand that all of these can play a role, and they can play a very important role in plant nutrition. So we definitely need some more rethinking, and here's just then a nice example of thinking about what is the most efficient form of nitrogen. Okay, so then we've done some great stuff with foliar nitrogen. We're using less. Maybe we're applying some foliar organic nitrogen, throwing some fish hydrolysate in with foliar urea. Great combination, okay, for example. And we've done really good on that piece of the puzzle. We're ready to kind of take a next step into substitution. Can we use microbials? And the thing about the ESR framework, when we think about the substitution phase, it is often considered somewhat of a vulnerable zone. And I think the nitrogen case study is a really good example of why this is. In this vulnerable zone of substitution, one of two things can either happen. You can either get stuck in the substitution efficiency phase, or you can break through into the redesign phase. And so it's considered within the transitional thinking somewhat of a vulnerable stage. And I think nitrogen gives a great example, because when we talk about nitrogen-fixing bacteria, we've touched a little bit on this earlier today in some of the questions. Of course, when we talk about biofertilizers and microbials, they have some big potential and big inherent problems. When we're talking about living organisms, microbials, we had the questions, how do you know what you're applying? Is it still alive? Is there any pathogens in there? How do we really know what we're doing? And absolutely, that is one of the challenges of biofertilizers. And I think that the nitrogen provides a really good example here where, yeah, if you go and apply a nitrogen-fixing bacteria, may not work for you, again, that's going to taint your experience with that, and you're may not progress down this transition into redesign. Look, that really didn't work for me. I'm going to go back to the foliar nitrogen. I'm going to go back to the artificial nitrogen. I'm not going to progress through that transition because in this vulnerable stage, it didn't work for me. And I think biofertilizers, as you all know, have somewhat of that reputation. They can be difficult to use. They can be inconsistent at times, and that is a big problem. I would also say that is a problem that we can overcome, and I think with this impulse into soil biology that's happening in all of the life sciences, and particularly in agriculture, of course, we have so many knowledge gaps when we talk about soil biology, especially microbiology. We have so many knowledge gaps. Once we fill those knowledge gaps, yes, I'm sure we can improve the consistency of biofertilizers. I'm sure they can be tools for the future, but sure, they have their problems at the moment. And I think that's a very good example of that. And ultimately, of course, we're interested in turning nitrogen gas. There's an abundance of it in the air. We're ultimately interested in turning that into a plant-available form. For that in its ammonia, which gets very rapidly converted into ammonium. But again, it's really important to be holistic in our thinking. There's other nutrients that are required for nitrogen fixation. For those bacteria to fix that nitrogen, to grab it from the air and deliver it to the plant, those bacteria require lots of other nutrients. We talk about plant nutrition and managing plant nutrition with all the essential nutrients. Well, microbes require those same nutrients, essential nutrients for them, for their health and function. And the same is true with N fixation. So the bacteria themselves, they need molybdenum, they need iron, they need nickel, they need phosphorus, especially these four for all N fixation. And if we were to expand to talk about legumes, legumes have the rhizobia in legumes need calcium, boron, cobalt, and copper. These are all essential. And if there is a limitation of any one of these, the potential nitrogen fixation will be held back. So again, holistic thinking here, we need to kind of manage whole systems and kind of manage all pieces of the puzzle. It's not just about, oh, I bought this product, oh, I'm going to go and apply it. You're setting yourself up for potential failure. You have to put the product within the system that is designed for it to work. And I think that's just a very nice, quick example of that. And so then there's a lot of opportunity here for N fixation. Sure, legumes are the king. I'm going to talk about them quickly now at the end. Legumes with rhizobia that can fix nitrogen within those nodules. But we also have what's called associative nitrogen-fixing bacteria. And these are nitrogen-fixing bacteria that can associate with any plant whatsoever. They can simply live on the root and around the root system, feeding off those root exudates and fixing nitrogen for any plant. There are many bacteria that we know that associate with cereals, that associate with oilseeds. They don't form nodules, they just live on and around the root system and still also fix nitrogen. So these are called the associative. And then we also have free-living nitrogen-fixing bacteria. These are bacteria that don't even need to be on a plant or with a plant and can still be fixing nitrogen. So there's potential, knowledge gaps also, but also lots of potential to harness some of these other nitrogen-fixing bacteria. But then really, I think the redesign is a good example to then bring the conversation back to legumes. Legumes, of course, are the kings of N fixation. They can do it the most, the best. So I think wherever we can redesign and bring legumes into the production system, the better. So let's have a quick look at that. We heard just a lot about diversity just then. We want to kind of transition from monocultural, simplified landscapes, from uniformity into diversity. And sure, that could be done in a whole host of different ways, from cash crops, wider rotations, novel cash crops, using annuals, using perennials, could be summer, could be winters. Cover crops, of course, a great way to kind of bring diversity into the cropping spaces. Companion and intercropping, I'm going to talk quickly on these. But again, other areas, non-productive areas, biodiversity strips, field margins, agroforestry we just heard about, arable silver pastures, all of these things. These are all great ways to diversify the farming system and therefore to diversify the landscape. And of course, we could have, in all of those lists there, we could be using legumes as part of that process. And therefore bringing in some of that free nitrogen, bringing in some of this redesign, building better ecological infrastructure to support wider landscape processes. And I think just to make this point about the substitution phase and why efficiency and substitution are important, but we must be mindful to not get stuck there either, is that, again, this example could be a great high efficient farm, maybe substituted out of inputs, using those biologicals, etc. That's all really good. But also one of the other negatives of that, beyond the fact that you can still see we have a very monocultural, simplified landscape, but one of the other negatives of being stuck in there is that as farmers, you're also still stuck in input dependency. You're still buying something. You're buying a biological now, and maybe that's better, but you're still stuck on buying an input. The thing about redesign is you are decoupling that input dependency. And that's why then, obviously, bringing in this example, legumes into the system, be that in the field or in the field margins, can be very advantageous. You're not just now, well, I used to be stuck buying fertilizer, now I'm just stuck buying this microbial bug. You still have input dependency. And it is redesign that is truly going to decouple, unshackle you from that. So, of course, we could use lots of legumes. I'm not going to talk too much on this, but just to say that, of course, there's a whole selection of legumes that you could potentially use to be integrated into any of that kind of list of from uniformity to diversity that we looked at. I'm not going to go into those. I'm sure you'd have great ideas yourselves. I think cover crops are just a great, also a really good stepping stone into this broader discussion about redesign. It's still within your cropping areas. It's benefits there to the cropping spaces, therefore to the rest of the cropping rotation. I think their cover crops are great. I'm glad to see that they're gaining traction all around the world, certainly especially here. And again, if we use legumes, we can bring nitrogen into the system, but of course, it's multifunctionality, that word again. We get so many other benefits from cover crops, to soil protection, to soil health, building soil organic matter, improving water, of course, water quality, improving infiltration, minimizing erosion, all of those kinds of things. There's benefits to the agronomy, where unlocking nutrients, cycling nutrients that can improve soil fertility, reduce dependency on fertilizers. We can use it to produce forage, lots of other benefits, and of course, certainly to the wider landscape, to the wider ecology, like the examples that we've just heard as well. Habitat creation, creating space for pests and for pollinators and predators to control pests, all of those things. So again, it's just, even though we're talking about legumes, we're talking about nitrogen, the reality is that in integrating them, we bring so much of this multifunctionality. There's so many other spin-off benefits to that. And okay, how then can legumes really help us reduce our nitrogen dependency? It is not just about growing legumes as cover crops to then terminate them, for them to die and decay and release all of that nitrogen. We can also share nitrogen in real time in the current season from the legume to the non-legume companion through things like companion cropping or through intercropping. And so, yes, a lot of the nitrogen is released as the legume roots die and the nodules decay. Yes, we get a lot of nitrogen released through that pathway. But also, as those legumes are growing while they're still alive, they are photosynthesizing, they are releasing root exudates. When we talk about root exudates, we're not just talking about sugars. There's a whole host of different root exudates that plants release, some of which are amino acids, peptides, proteins. those organic forms of nitrogen that we were talking about before, they are root exudates. They also get taken up by the plants, but they also get excreted by the plants as root exudates. So when we have a legume root system and a non-legume root system kind of growing side by side and intermingling, that legume is releasing amino acids as root exudates. And that non-legume companion can scavenge those, can absorb those and take them up. So we can get direct sharing of organic forms of nitrogen, of amino acids predominantly, but again, some proteins and things, through root exudation and then being taken up. And if the two plants are also both mycorrhizal associators, they can, if they are connected through common mycorrhizal networks, again, it can be amino acids that get shared from the legume through the mycorrhizal hyphae and delivered directly into the non-legume. So we do have these two other pathways of real-time, current season sharing of nitrogen from legume companions to non-legumes, to the cash crop, to the cereal, to the oilseed, whatever it might be. So there is potential. Now, is this fully and truly optimized currently? No. Is there knowledge gaps? Could we make this better? Yes. Some varieties are better at doing this than others. For example, other agronomic traits, little leaf clovers are better at sharing nitrogen because bigger leaf clovers have a higher nitrogen demand to grow that bigger leaf. So they hold more nitrogen back and they share less. A little leaf clover needs less to grow that little leaf, so it can share more. There's many variables to optimizing this process, for sure. And again, with good science and research, we could answer more of these questions and really fine-tune and optimize this process for greater potential, for sure. It's early days. And even fascinating examples, we think about plants always so competitive against each other. They're competing for moisture, competing for nutrients. We are beginning to see examples of where plants actually are very collaborative and they work with each other and support each other. Here's an example here where this study showed that maize, in this example, released, this is from the maize released a couple of root exudates that activated the rhizobia in the soil. Now, of course, maize can't form nodules and form that association, but it was able to wake up and activate the rhizobia in the soil. Some of its root exudates were able to do that, and it had some other root exudates that also ultimately supported the nodulation process. So we have an example here where the maize is releasing two very specific exudates that is helping the faba bean fix nitrogen. Why would it help it? Surely this faba bean is robbing other nutrients, robbing moisture, making it harder for the maize to grow, isn't it? But clearly it is doing that to help the legume because there is this nitrogen transfer back and that the maize can benefit from that greater nitrogen nutrition, greater biomass, greater yield, which is what they observed. So again, we have these emerging examples in the literature of very specific interactions that, again, once we uncover these blind spots of knowledge, yes, we can redesign the system to be even better and really help us in this whole transitional discussion. I'm probably getting tight on time, aren't I? So I'm going to skip through this one. It's just to say, as the title says, intercropping is like a whole lot of other multifunctionality and good benefits. So they showed here that it increased soil carbon content 4% over sol crops, and that it increased soil nitrogen by 11% over sol crops. So improvements to soil health, to soil carbon, to soil nitrogen levels. Of course, that's all good. This was a quick study just to share that the benefits or the interactions of mycorrhizal fungi. I gave that example before, how through the mycorrhizal hyphae we can get sharing of that nitrogen from the legume to the non-legume. And really this study was just highlighting exactly that actually when we have bicropping or companion intercropping, that actually we see mycorrhiza respond positively to that greater diversity. So when we have faba bean mixed in with some wheat, we get greater mycorrhizal colonization. When we have some beans mixed in with wheat, we also get greater mycorrhizal colonization. But this also translates then into nitrogen fixation. This is nitrogen derived from the atmosphere. And you can see here under a monocultural situation with or without mycorrhizal fungi, both plants pretty much, the legume was fixing the same amount of nitrogen, be that if the legume was with a wheat companion or as a monoculture. But as soon as we put it in a monoculture and also added mycorrhizal, so added the bridge between those two companions, you can see here we get a jump up in the amount of nitrogen fixed by the legume. So the point summary here is just to say that the legume will fix more nitrogen when it is with a wheat companion than with mycorrhizal, that mycorrhizal bridge intact, versus that being in a monoculture without that mycorrhiza. So just highlighting a link here with the biology, and that they also play a role in enhancing this process and supporting this process. What about some above ground benefits? This is a study from France, so fine, take it with a grain of salt, but just very interesting one to share anyway. This is comparing again a wheat and a bean companion intercrop here. And we can see here we're looking at the wheat yield, intercrop in grey, sole crop, monoculture in the white, across 3 different years. And you can see here that the wheat yield is higher in the grey bars when that wheat was grown with a bean companion. Okay, so the bean there is obviously helping, supplying that nitrogen. So we saw increases in the grain yield of wheat when it has a bean companion versus a monoculture wheat. But if we then also look at protein, because protein and yield are a trade-off, aren't they? As yield goes up, protein goes down. As protein goes up, yield goes down. If we then look at protein of that wheat, we can also see that actually when the wheat was grown, again, with the legume companion, so in the intercrop, in the grey bars, we can see we also got a significant increase in the protein levels across 3 years. So the wheat had higher yield and higher protein when it had a legume companion versus not legume companion. So there was not this competition and robbing of moisture and nutrients and yield reduction for the wheat. Actually, we enhanced yield and we enhanced protein by having the legume companion there. And last slide, I'll wrap up here. This is in a pasture situation, just trying to give a few different examples of how, when we integrate legumes into the system, they can help us with this nitrogen piece of the puzzle. So here we're looking at a monoculture of perennial ryegrass with a couple of different nitrogen application rates. And then we have a more diverse mix. So this is just a 4-way mix. With that perennial ryegrass, we had some timothy and red and white clover added. And in mix 2, we then additionally had plantain and chicory added. So let's just quickly point this out. Here's our monoculture of perennial ryegrass, a couple of different nitrogen rates. So at 0 nitrogen, here's our baseline. This is the potential tonnage yield, biomass yield, dry matter yield, that we can achieve with a monoculture at 0 kgs of nitrogen. Here's our baseline. Now, of course, as we add a bit of nitrogen, we get some nice increases thereof. However, if we come over here to our mix where we had those 2 legumes also added in, 1 red and white clover, okay, also 0 kgs per hectare, we have more than exceeded our baseline simply by having the legume there. Okay, both of these have significantly out-yielded at 0 kgs of nitrogen. So what about over here then? Once we added 120 kgs of nitrogen, here's what we got in terms of monocultural ryegrass yield. If we follow this line, come over here, still in our mix 1 at 0 kgs of nitrogen, we have still out-yielded 120 kgs. We have still out-yielded it with 0 kgs of nitrogen added, and same again with our next mix. So let's go up again, 240 kgs of nitrogen to monoculture ryegrass. Here's our yield. If we then follow this one across, okay, now we're just under, remember this is 0 kgs, we are just below the same biomass as 240 kgs, but if we come over here to our mix 2, you can see following that line at 240 kgs, here we are on par at 0 kgs of nitrogen, we are on par with 240 kgs of nitrogen simply by having a little bit of diversity in the mix. 2 clovers, another deeper rooted grass, and a couple of deeper taproots. Okay, so again, just very nice example. This is on a multi-species sward, this is from Ireland, on how we can use redesigned diversity to help us lower our nitrogen requirements. So in summary, strategies to improve nitrogen sufficiency. Of course, this is really important. We all know about this. We're trying to reduce our dependency on bagged N. We can use things like foliars as one example that I gave, but sure, it could be other stabilizers and inhibitors, all those other kind of things potentially. Lots of tools in the toolkit for sure. We could use nitrogen-fixing inoculants, as I mentioned. They can play a substitutive role, and they can be easy to use. Seed treatments, furrow inject, a range of endophytes, bacteria that live inside the plant, inside the leaves, that can also fix nitrogen. So there's a lot of potential in that space, but I will acknowledge also knowledge gaps. And then legumes, ultimately, they are the supreme and fixers, so wherever we can use them, cover crops, companions, rotational age, pastures, etc. And in closing, let me just leave you with this thought. If we think about this process of transition and making changes to our farming system, the broad kind of theme of the conference, there's a lot of kind of raging debate about how do we go about this. Do we take kind of these small steps, these incremental steps, low risk, definitely good safe strategy, taking small little steps, this is called incremental change, or little bits of evolution, step by step. But many feel that this is not enough, and this is kind of that example of getting stuck in the efficiency and the redesign phase. Many people say we need not evolution, we need revolution, that we need transformative change, transformative level change. We need complete change, complete system redesign, that taking little steps is not enough. And a really good example to kind of think about this process is Edison, he didn't invent the light bulb through incremental change of the candle. He didn't just tweak the candle and tweak the candle and tweak the candle and tweak the candle and advanced the world of lighting. No, he just did complete redesign. He completely did transformative change and out-of-the-box thinking completely changed what we're going to do. And that's a really nice example of what many say we need in this discussion about transition, that we need transformative change, and here's a very nice example. Now, even though he did that, and that's a nice example of that, what's happened, of course, since to the light bulb? Well, okay, from our old incandescent light bulb, now we've gone through incremental change, step by step, piece by piece, to get to a modern LED light. Or again, we've gone through that efficiency stage, taking it, tweaking it, tweaking it. So I think it's a really nice example to say it's not necessarily that incremental change is bad. I think there's a really nice example of how it can be used for good and improve something that can be improved. But it's also to say let's not also neglect the potential. Let's not get stuck in incremental thinking, because sometimes we just need out-of-the-box thinking. Sometimes we need that transformative or revolution change, which indeed can also be very advantageous. Okay, thank you very much.